Hello everyone, my name is Ami Mohammed, and today I'm excited to present our paper, Accio Rethinking OS Architecture Co-Design for Next Generation I/O. This is joint work with my advisors, Professor Manohar and Professor Soleil at Yale University. So we love OS abstractions, but they are slow. In the recent years, we have seen a great performance improvement in I/O devices. We now have network devices that can support 800 gigabits per second and even more. Meanwhile, single-thread CPU performance has largely stagnated. We have reached the end of 10 hours scaling, and we do not expect to see much improvement in a per-core CPU performance anymore. As a result, the operating system abstractions that were designed decades ago with slow I/O devices in mind and were once low overhead are now sitting in the critical path of I/O. But what is the difference between these conventional abstractions and the high-performance ones that we have for I/O programming today? So here are the two ends of the I/O design space. On one side, we have the POSIX API that prioritizes ease of use. You can use POSIX and create a socket and use system calls such as open, close, read and write, exactly like working with a file, to send and receive messages over the network. And by doing that, you let the OS handle device multiplexing, memory management, and header processing. On the other side, we have kernel bypass platforms such as DPDK that favor performance. In these systems, most complexity is pushed out of the kernel, out of the OS, and into the application. And the application developer has to now configure the device, set up the queues, and use polling APIs to receive messages from the network. Here, kernel is bypassed. And this naturally raises a question. How different are these two abstractions, these two ends of the design, IO design space in practice? So first, let's talk about the kernel-based network stack. Consider this system architecture that we have a NIC, we have a CPU and memory, and the CPU is running either on kernel mode or in user mode running an application. And the memory is divided between the kernel and the application. And now consider this simple example. This application that creates a socket and uses a read system call to receive data from the network. This system call will go to the kernel and will wait on the socket to get some data. And whenever the NIC receive a packet, it will do two things. It will first copy the packet into the kernel buffers, and it will fire an interrupt, letting the kernel know that the packet has arrived. And the kernel will then get the packet, processes its headers, finds the socket and application corresponding to the packet. It will copy the packet into the user memory and runs a context switch to give the control back to the application. And now the application can read the data. But what are the overheads here? And where is the time being spent? To figure this out, we ran a detailed breakdown experiment. It turns out from the time that the packet arrives at the NIC until it reaches the kernel, it accounts for 25% of the time. Roughly 15% of the time is spent on header processing in the kernel, and a significant 60% portion of the total latency is spent on context switching and copying from the kernel memory to application memory. So a lot of prior works have tried to optimize different components in this pipeline. One class of work would focus on using um, hardware accelerators and offloading engines to put more functionalities into the NIC instead of the OS. Another class of work would focus on optimizing the operating systems um, themselves by using techniques like zero copy IO. But the one approach that gives you the best performance is kernel bypass. And kernel bypass does that for us by giving direct access to the IO device to the applications. And by doing that, it basically eliminates two things in the breakdown that we had. It will eliminate user space delivery and header processing. And now we are only left with the time that the packet takes to travel between the NIC and the CPU. Kernel bypass has some limitations too. We need to put a lot of burden on the application developer. But what does it actually get you? What does kernel bypass buy you? To answer this question, we ran a simple ping pong experiment between two directly connected servers. This figure shows the distribution of round trip times, round trip latencies for applications written using DPDK and OS sockets. And we can see that DPDK applications achieve significantly lower latency compared to the OS sockets ones. However, this performance comes at a cost. And when we try to add back the features that are eliminated from the kernel, like multiplexing, we start to lose performance. We can see that we can lose 20% of the latency by adding a simple feature like multiplexing. And this raises an important question that is there a fundamental trade-off between ease of use and performance, or can we have both? So we were wondering if we can get kernel bypass performance and POSIX APIs together. So to find an answer, we look to a successful precedent in computer systems, that is virtual memory. So virtual memory that has been evolving for more than 40 years now. It provides an abstraction that is both safe and high performance using a CPU memory and OS co-design. It gives the applications indirect memory access, but with the performance similar to a direct physical memory access. And it does that by introducing this hardware structure called TLB that caches page tables and translations, and the OS manages core data structures and the TLB. And our key insight is that virtual memory, in the common case, avoids of the OS, avoids the kernel, but goes to the OS for exceptional cases. But how can we do the same thing for I/O? And this leads to our proposal, Accio, which is a novel software hardware co-design that achieves high performance I/O and preserves POSIX programming model. So prior works usually are reluctant to change the CPU. But we introduce small but important changes to the CPU microarchitecture and leverage the unique hardware as an accelerator to offload header processing, transport protocol processing to it. And finally, we modified the OS to support our new features. So far we've discussed prior work and motivation behind Accio. Now let's look at the Accio design in more detail. Let's revisit the system architecture. We still have the NIC, the CPU, and memory with a clear separation between the kernel space and user space. First, we introduced two new things. First is a user space library that provides a POSIX compatible API to our applications. Second, we leverage the NIC as a hardware accelerator and offload the transport protocol processing to it. So we basically do all the header processing in the NIC hardware and not the kernel anymore. Now, for connection setup, applications can use similar APIs like sockets um, to talk to Accio library and create a connection. And here, since we want our applications to have direct access, fast access to important informations about the connection, we introduce a new hardware structure called the I/O connection table that holds very essential information about the connection and its associated process. And this structure can be directly accessed from the application, but is mainly managed by the OS. So, and this looks like a TLB basically. And when a socket is created, the kernel will populate an entry about its connection and the process into the I/O connection table. Now let's consider a read operation in Accio. So there are two cases for a read. We are either in a fast path or a slow path. So in the fast path, we assume we already have some data at the NIC that we want to read. So when the data arrives at our NICs, our modified NIC is able to communicate with I/O connection table, letting it know that a new packet has arrived and get some information about it. And it will copy the packet directly to the application memory using those information. And after we issue a read command, our library will communicate with the I/O connection table, understands a packet exists right now for us, so it will read it directly from the memory. And note that here, since we are not doing any system calls, we get exactly kernel bypass performance. But what happens if there is no data at the NIC already? In this case, we again call the read. Our library will talk to the I/O connection table, but here we want it understands no packet has arrived. So in order to maintain the same blocking APIs as before, we have to suspend the application. So we go to the kernel, we ask the thread scheduler to do that for us. And here we want to have a way to actually let the application wake up immediately after a packet arrives. So we introduce another hardware structure called the I/O ready queue that gets updated by both the thread scheduler and the I/O connection table and acts as a cache for ready to run threads informations. So when a packet arrives at the NIC will again notify the IO connection table about it and will DMA the packet to the application memory. But now, since our application is suspended, it will also trigger an interrupt. And in the kernel, our thread scheduler will check with the IO ready queue, which is updated from IO connection table now, and understands that, okay, our application is able to wake up and it will immediately do a context switch, give the control back to the application, and our application will eventually read the packet, read the data. And here we are using optimized interrupt delivery systems and hardware assisted scheduling. And these two will allow us to have almost immediate wake ups for our applications. But why do we need CPU changes here? So the core problem is that user space needs some information about the connection, but not full control. And because applications need to know if the data is available and where the RX and TX buffers are. At the same time, OS must control everything, and the NIC must be able to update these informations as well. And existing CPU abstractions just don't give us a clean way to do this. And this is the reason why we argue for modest changes to CPU microarchitecture. So the remaining question is whether this co-design actually delivers lower overhead and better performance in a real system. To answer this, we built a full hardware software prototype and evaluated Accio. We integrated Accio into an open source RISC-V rocket core and implemented both the NIC and the CPU on the same FPGA. Our Accio design consists of approximately 3,600 lines of chisel code, and it allows us to evaluate the complete system under realistic conditions. Note that our FPGA runs at 50 megahertz, and we only have a simple CPU microarchitecture. But a typical server runs at higher clock frequencies and has advanced CPU microarchitecture. So to account for these things, we scale our measurements in two ways. One is a 40x scaling based on um, clock frequency, and the second is a 200x scaling that also accounts for microarchitecture differences. And note that we only scale the execution time that occur on the FPGA. So if we send a packet and receive the response, we timestamp all the packets, and we only scale the regions that actually occur on the FPGA. And we now present our evaluation results. We begin with packet processing latency. We use a UDP ping pong benchmark for this, and we can see that at a 40x scaling, Accio achieves latency comparable to RDMA. In a realistic setting, we expect our performance to lie between these two curves of 40x and 200x, but we expect it to be more close to the 40x estimate. But overall, Accio improves latency by 31% compared to DPDK applications and also preserves POSIX API. Next, we evaluated throughput. We used the UDP workload for that, and we saw that Accio can saturate the FPGA bus bandwidth, which is lower than that of the modern servers, but still we expect Accio to saturate a 100 gigabit per second link in a realistic deployment. And finally, we examined CPU utilization using an Accio-based UDP server. We can see that actually we observed up to a 66% reduction in CPU usage compared to kernel bypass systems such as DPDK or RDMA. And in many cases, Accio also outperforms traditional sockets in CPU utilization. And in summary, we presented Accio, which is a system that preserves familiar POSIX abstractions for us and also achieves kernel bypass performance. Our proposal, Accio, modifies the CPU microarchitecture and provides a hardware-software co-design for I/O, inspired by virtual memory and TLB. We introduce an I/O connection table and an I/O ready queue to enable fast process wake-ups. We also use hardware-assisted scheduling and optimized interrupt delivery systems to improve the performance and let us match the kernel bypass systems. And finally, using an FPGA prototype, we showed that Accio can achieve low latency, high throughput, and reduced CPU utilization. Thank you for your attention, and feel free to reach out using the contact shown in this page. Thanks.